Our next unit in chemistry and also in conceptual chemistry is on bonding and intermolecular forces. This video will focus on the concept of electronegativity and bond character. Looking at your learning standards and targets for this unit, we are working on the essential standard for the unit of being able to model and describe chemical bonding. And this particular video will just focus on the first of these learning targets to define electronegativity and use it to identify bond character. So electronegativity, this is something we viewed a little bit and learned a little bit about in our periodic trends learning. Recall that electronegativity is the attraction for electrons in a chemical bond. And the trend in this we can see on a periodic table. Now this is a bit of a different way of depicting it using a color scale, where the most electronegative elements we see are listed here in orange and yellow and red. We see those here towards the top right hand side of the table, and then as we get towards green, light blue, and darker blue, as we work down towards the left here, the bottom left, those are lower electronegativities. So just keep in mind throughout this that remember that nonmetals, these elements here on the right side of the table, have higher electronegativities. They have a greater attraction for electrons in a bond, whereas metals here on the left side of the periodic table have lower electronegativities. We also want to recall ionic and covalent bonding. Again, something we've looked at a bit so far in our learning, but we'll look at in much more detail in this unit. Recall that we have said ionic bonding comes from the transfer of electrons to form oppositely charged ions. So for example, if we were to show how an ionic bond between sodium and oxygen form, we might draw a diagram that looks something like this, where we see sodium with its one valence electron will give up a valence electron to oxygen, and we need a second sodium to fill oxygen's octet. And so we might say this, where sodium gives up its valence electron to oxygen, forming these charged ions, the sodium ions, the 1+, and the oxide with that 2- charge there. And we've said covalent bonding is the sharing of valence electrons for mutual attraction. So for example, if we were to bond two chlorine atoms together, each of them has 7 valence electrons, so they need one more. They could share a pair of electrons where each nucleus of the atoms of each chlorine atom is attracted to that same shared pair of electrons, and that's how we've defined a covalent bond. Well, as it turns out, though, once we start considering this idea of electronegativity, this idea of bonding, ionic and covalent, is not so black and white. There's a very gray area in between that we will see here. As it turns out, electrons are not completely transferred from one atom to another in ionic bonding. So if we consider this example again that we just had on the last slide of the formation of sodium oxide, where we might draw a diagram showing sodium giving up a valence electron to oxygen. The thing is that electron that we're showing the sodium giving up or losing, it's actually still being attracted to the sodium atom. The sodium atom still has some pull on that electron. Why is this, you might wonder? Well, it's because sodium still has a non-zero electronegativity. If you look at your periodic table, find sodium and look at its electronegativity, you'll see its electronegativity is listed there as 0.9. It's not 0. So that electron that we show going from sodium to oxygen is not just gone forever to sodium and have nothing to do with it. It's still pulling on that electron some. So there's not a total transfer of losing an electron to oxygen. In other words, what we're saying here is think of bonding, of any type of bonding, especially with ionic and covalent, as really a game of tug of war between atoms for these electrons. Where if we look at the electronegativities of the two atoms involved here, oxygen and sodium, we'll see that oxygen's electronegativity, which is 3.5, you can see that on your periodic table, it is much greater than sodium's, which is only the 0.9. So there is a large difference between those electronegativities. So this means that the electrons in this bond are not shared very equally. In fact, they're shared very, very unequally. So unequal, in fact, that we simply say that the electrons are transferred from sodium to oxygen, and we call the bond ionic. In other words, what we're saying here is there actually is no such thing as a 100% ionic bond. What that would mean is, if we did have a 100% ionic bond, if we think about the example we're using here, where sodium would give up a valence electron to oxygen, and the sodium would have absolutely no attraction for that electron anymore. Well, that's not the case, because sodium's electronegativity is not zero. In fact, if you look at the periodic table, you will see that there are no elements listed with an electronegativity of 0. Now notice that is different, though, than the elements that simply don't have an electronegativity. That doesn't mean their electronegativity is 0. All that really means is they don't form bonds. So if they don't form bonds, then they simply don't have an electronegativity. It's not that that value is 0, there just isn't a value there, period. The big idea here, you might be wondering, well, we're talking about large differences in electronegativity. How big does the difference have to be in order for us to consider a bond to be ionic? Well, that number is 1.8. If the difference in electronegativity between the two atoms is greater than 1.8, we consider the bond to be ionic, because the sharing is so unequal between the atoms that it's as if one atom simply gives up an electron to another. Notice the difference here between sodium and oxygen's electronegativity would be 2.6. The difference between 3.5 and 0.9 would be 2.6, so that is greater than 1.8, so we consider this to be an ionic bond. Let's consider this same thing with what we know about covalent bonds. Now, we just said that electrons are always shared to some extent, even in ionic bonds. But electrons actually can be shared perfectly equally, though. Consider this, a bond between two chlorine atoms. We looked at that example a bit earlier. Now this is a different diagram here. Because this bond is between atoms of the same element, these electrons will be shared perfectly equally. This is because these atoms are the same element, they will have the exact same electronegativity. And thus, these two atoms, the two chlorines, will have the exact same attraction for these electrons in the bond. So if you look up here at this picture, the diagram of this bond between chlorine, this pair of electrons here in the middle, I know it's kind of hard to see there, the yellow and the orange dots, is getting pulled equally in both directions by the chlorine. Now, one thing that we want to clear up here with this picture, doesn't do a great job of showing, is these electrons that are being shared here in the middle, they're not actually stuck directly in between the atoms. They're free to move back and forth between the two atoms, but because the electronegativities are the same, they will spend just as much time around this chlorine atom on the right as they do the chlorine atom on the left. So we say that the electrons are shared perfectly equally. This is a 100% covalent bond. Because these two atoms are the same element, they have the exact same electronegativity, they will be shared, the electrons will be shared perfectly equally. Now, one other note about this idea of a perfectly equal sharing, this would only occur when we have two atoms of the same element. Even though if you look at your periodic table, you will see different elements have the same listed electronegativities, they are not exactly the same. Those values are rounded to the tenth place. So even though you might see two values that do appear to be the same, they are not identical in their electronegativities. So while the electrons between those atoms might be shared very equally, they would not be shared perfectly equally, and thus we would only get a 100% ionic bond when we are bonding atoms of the same element. So what if the electronegativities of the atoms that are bonding are close, but they're not exactly the same? So let's consider a bond between hydrogen and chlorine. And I'll talk about this picture up here in just a second and tell you what we're seeing here. But just look at the electronegativities of those two. The electronegativity of hydrogen is 2.1. Again, you can find that on your periodic table. Chlorine is 3.0. So the difference between the electronegativities is just 0.9. So that's not nearly high enough to be considered ionic. Recall our threshold for that is a difference greater than 1.8. So the bond's not ionic because the difference isn't big enough, but yet these electrons are not being shared equally. Chlorine's electronegativity is higher than hydrogen's. So these electrons that are being shared are not going to be shared equally between the two atoms. The chlorine, because it has a greater electronegativity, will hog those electrons a little more than hydrogen. It's going to be unequal sharing. This leads to what we call a polar covalent bond. And what we're seeing here in the diagram will explain this idea of a polar covalent bond. Notice this kind of oblong shape around our hydrogen and chlorine. The size of this shape here is used to represent the electron density. In other words, how much time this shared pair of electrons spends around each atom. And notice the size on the chlorine size is bigger. This is because these electrons that are being shown in the middle here are going to spend more time around the chlorine than they do around the hydrogen. Again, this is because chlorine has a greater pull on those electrons, because its electronegativity of 3 is greater than hydrogen's of 2.1. Now, not so much greater that it simply takes the electrons, or what we would say takes the electrons, like in an ionic bond, but enough that we would definitely say that it's unequal. Because the electrons are not being shared equally, again, the electrons will spend more time on the chlorine end of the bond than the hydrogen, that's going to make the chlorine atom partially negative, and that's this notation you see out here to the right by my cursor here. That's the lowercase Greek letter delta that you see there, and then the negative charge there, showing that the chlorine is a partial negative charge, whereas the hydrogen is a partial positive charge, because it's losing some electron density to chlorine, and chlorine's gaining the electron density. So just to review what we've said here about polar bonds are bonds where the electrons are not shared equally. These electrons that make up this bond are getting more attracted to the chlorine than to the hydrogen. And these polar covalent bonds will result in partial charges that we see here in the picture that I referred to just a bit ago. So how do we keep all this straight? Ionic, covalent, polar covalent, differences in electronegativity. Well, here's a simple schematic to help us understand this stuff. A couple things we're looking at here. So at the top here, we just have some words to describe the differences in electronegativity between bonded atoms, where there's zero electronegativity difference, an intermediate difference, or a large difference. And then the type of bond, or what we call the bond character, here to go along with it. Where if it's zero difference or really close to zero, as we'll talk about in just a second, we call that a covalent, or simply a pure covalent, or a non-polar covalent bond. If there's a moderate amount of difference, we call it polar covalent. And if we have a large difference, that would be an ionic bond. Now, what do these differences have to be to fall into each category? Well, we see that down here. If the difference is 0.4 or less, then we consider it to be a pure covalent, or what we call a non-polar covalent bond. So the electronegativities don't have to be exactly the same. If they're close, 0.4 difference between them or less, the electronegativities are so close that those electrons are shared very equally. And so we consider the bond to be a non-polar covalent bond, where the electrons are shared equally. If the difference is somewhere between 0.4 and 1.8, that's when we have a polar covalent bond. That's the example we just looked at before, where the electrons are not being shared equally, where one atom gets more electron density than the other, causing us to have those partial charges. And then if the difference is greater than 1.8, that's when we get the ionic bonding. Whenever we have a difference so great that we say the electrons aren't shared anymore, they're transferred, and we get those full positive and negative charges. Here's another good summary. A couple of these pictures you've already seen part of before, where if we have a non-polar covalent bond, that's when the difference in electronegativities is very small, less than 0.4, and these electrons get shared equally. Then we have a polar covalent bond here where the electrons are not shared equally, where the density is greater for one atom than the other. This is when we have that moderate difference in electronegativity, again somewhere between 0.4 and 1.8. And then we have our ionic bonding situation where the difference is so large that one atom simply just takes the electron from the other, or at least that's how we describe it, and that gives us full charges, resulting in ions, where we have a full positive charge and a full negative charge that you're seeing here on the sodium and chloride ions. So I've used this term bond character a little bit, and it's actually in our learning target, define electronegativity and use it to identify bond character. Here's a graphic that can help us understand what we mean by bond character. So along the bottom, this axis here, we're graphing the difference in electronegativity between atoms that are bonding. And then on the vertical axis here, we are graphing percent ionic character. In other words, if we had a 100% ionic bond, and actually there is no such thing, you'll see none of the data points are up here, but if we did have a 100% ionic bond, that would mean the electron is completely transferred from one atom to the other. And if we have a 0% ionic bond, that means the electrons would be shared perfectly equally, because that would mean 100% covalent. So notice this is not a perfectly straight line. It's not a perfectly linear relationship. But what we can do is this. If we put a line there going vertically through that 1.8 number that we talked about earlier, we'll see here that atoms that bonds to the right of this, these would be between, notice, mostly between metals and nonmetals, lithium fluoride, potassium fluoride, cesium chloride, etc. These are the ones we consider to be ionic, and notice that they have an ionic character of greater than 50%, so that would make sense. Whereas bonds to the left of this 1.8 line, these are where the electrons would be shared a little more equally, where it's less than 50% ionic character, meaning more than 50% covalent. And we can see that those are typically bonds between nonmetals with other nonmetals because they have similar electronegativities. All right, a series of review questions here. After each question pops up, pause the video, answer it yourself, and then play the video and see how you did. Question number 1, what is electronegativity? Electronegativity is the attraction atoms have for electrons in a bond. Question 2, why does the difference in electronegativity between two atoms in a bond need to be considered to understand the bonding that occurs? The difference in the electronegativity of the atoms in the bond will determine how equally or unequally electrons in the bond are shared. The degree of sharing electrons will determine the bond character, meaning is the bond nonpolar covalent, polar covalent, or ionic. Why is there no such thing as a 100% ionic bond? A 100% ionic bond would be the result of an atom giving up an electron or electrons and having zero attraction for those electrons. This will never happen because there are no elements that have an electronegativity value of 0. Those don't exist. Question number 4. Suppose a bond formed between each pair of atoms below. Determine the difference in electronegativity between the atoms and then the bond character of the bond, meaning nonpolar covalent, polar covalent, or ionic. You may need to flip back to the video and look at that table that had those differences in electronegativity values along with the bond character. So for this first one, we have sodium and fluorine. If I look at the electronegativities of those, you'll see that the difference in the electronegativity between sodium and fluorine is 3.1. This is greater than that 1.8 value, so this makes the bond ionic in character. In other words, the sodium, we're going to say, simply gives up its valence electron to fluorine because the sharing is so unequal. B, iron and sulfur. The difference between those two electronegativities is 0.7. So that's less than the 1.8, so that makes this bond covalent, but it's polar covalent because that difference in electronegativity falls between the points, the 0.4 and the 1.8. So in other words, the electrons are being shared, but not real equally, where the element with the higher electronegativity, which is sulfur, it's going to pull on those electrons a little more than iron, so that's going to give the sulfur that partial negative charge, the iron that partial positive charge. All right, C, carbon and hydrogen. The difference in the electronegativity there is 0.4. Carbon is 2.5, hydrogen is 2.1. So they're close together, and that's right on that 0.4 mark. That's considered to be nonpolar covalent. That 0.4 marks the cutoff. If the difference is 0.4 or less, then we have a nonpolar covalent bond because the electronegativities are so close that we consider the sharing to be equal. And then finally, we have iodine bonding to iodine. Here the difference is 0 because it's the exact same element. So this is going to be another nonpolar covalent bond. In fact, we would say this is a 100% covalent bond. It is perfectly covalent. The electrons are shared perfectly equally because those electronegativities are identical. All right, last few review questions here. Question 5. What is a polar bond and when do polar bonds occur? So recall a polar bond is a bond in which electrons are shared unequally. This occurs when the difference in the electronegativity between the bonded atoms is greater than 0.4. Question 6. While not usually categorized this way, ionic bonds are simply extreme examples of polar bonds. Explain why. So if you think about what we just said in the last answer, polar bonds are whenever electrons are shared unequally. Now, ionic bonds, this occurs whenever we have electronegativity differences greater than 1.8. So the electrons are shared very unequally. In fact, so unequally that we simply say the electrons are transferred from one atom to another and not shared between them, because that sharing is so unequal that we just say one atom takes the electron or gains an electron, another loses an electron, but it's really just an extreme example of a polar bond. Question 7. Compare and contrast polar covalent bonds with ionic bonds. So both polar covalent bonds and ionic bonds result from unequal sharing of electrons, kind of going back to that last question there. There's one atom that has a greater electronegativity than the other, so the electrons are not shared equally. However, the sharing in ionic bonds is so unequal that we simply say electrons are transferred from one atom to another. This results in ion formation, where if one atom gains an electron, it will now have a full negative charge. The atom that loses electrons will have a full positive charge. In polar covalent bonds, electrons are not shared equally, but more so than in ionic bonds. So even though one atom's pulling on the electrons more than the other, there's more of an equal pull compared to ionic bonds. So the result of this is that we just get partial charges on the atoms. The atom with the larger electronegativity will pull on those electrons a little more, so it's going to have a partial negative charge. It doesn't fully gain the electrons, so it's not a full negative, a partial negative charge. The atom with the lower electronegativity will thus have a partial positive charge because it's losing some of that electron density, not all of it, because it's not completely losing the electron. All right, in this video we've looked at electronegativity and we've used that to define bond character.